Swayam Prabha. Digital India. Educated India.
Welcome back to the lecture series in bioelectrochemistry. So, in the last class we were talking about the different kind of electrodes, and I mentioned about metal electrodes and ion selective electrodes. So, what I thought that let us think of a situation where really the biological component of electrochemistry comes very handy. So, if you see a critical care profile in a hospital, there is something very interesting you will observe. So, let us start the lecture today. So, this is our lecture 17, 19, 20, okay. And this is our week 4, lecture 2, so W4/L2. Okay. So, now if you see a critical care profile in a hospital, so you will observe something very interesting, and we will come back to the electrode concept from there, exactly the application part of it. Okay. So, the function and analyte. So, function, say for example, conduction, if we talk about nerve conduction. Okay. So, when you talk about nerve conduction, there are nerve conduction or conduction of cardiac conduction. So, we talk about Ca plus and K plus, right. Now, if we look at the muscle contraction or nerve contraction, cardiac muscle contraction. So, we talk about Ca2 plus, sometime magnesium. Okay. Now, we talk about energy metabolism or energy level. When you look at energy level, we look at glucose, we talk about oxygen, we talk about lactate, we talk about hematocrit. Okay. Then, whenever we talk about acid and base, so what is the level of acidity in the body, and we talk about pH, talk about PCO2, partial pressure of carbon dioxide. Okay. When we talk about osmolarity of the blood, which is, by the way, osmolarity of the blood is around 320 milliosmol. Okay. Osmolarity, we talked about sodium plus glucose. Okay. So, if the glucose level goes up, the osmolarity will go up. Okay. Then electrolyte balance, if we talk about electrolyte balance, then we are looking forward to Na plus, potassium, calcium, magnesium. Okay. Then, when we talk about the renal failure, we look for blood, urea, nitrogen, creatinine. A doctor needs to look at all these parameters as soon as a person comes in critical care unit, or even on a day to day, like whole body checkup. These are the things they look forward to. What is interesting for a bioelectrochemist, if you look at it? Interesting part for the bioelectrochemist, why you should study this subject. So, we are almost closing in, and I needed to share this very clearly with you, why you really needed to look at it. Because if you look at all these things, the chart what I have just now prepared for you, these are, could you recollect something? These are the simple ions which either by accepting an electron or by donating an electron, there is an E0 value which could be created. Now, if you just put your imagination, because we won't be able to cover all of them, but I wanted you to imagine if these analytes can accept an electron and change its gets reduced, or donate an electron gets oxidized. So, essentially using that analyte, if I have a standard, I can calibrate a standard, and any further addition will lead to a change in either the potential or the current, either the voltage or the current. Keep that in mind. That is the most important part. So, say for example, I say that suppose what we will be dealing. So, in this rest of the course, what will be, we will talk about, so I am just underlining, just a little bit off, we will underline how a glucose electrochemical sensor works, how a oxygen electrode works. Okay. We will definitely talk about these two, how the pH electrode works, we will talk about the third one. Okay. So, we will pick up some of them. Of course, there is huge amount of body of work all over the place, but if I give you some of these examples, that will kind of give you an idea how to look for the other ones. Okay. Now, the previous class, when I told you that you have two different kind of electrodes, you could have a metal electrode or you could have an ion selective electrode. When I say ion selective electrode, then I am talking about these kind of ions, analyte, sodium, calcium, potassium, magnesium, okay, HCO3. Now, if you have a sensor which could sense that particular binding of that ion and it gets reduced and change the potential, you should be able to determine its quantity with respect to a known quantity. Okay. So, keep this in mind, and in terms of the ion selective electrode, if we talk about what are the different ion selective electrode which are there currently with the technology, they are of this kind: ion selective electrode are of these different types. Say for example, one of them is the glass electrodes, which are used for H plus and certain monovalent cations, for H plus and certain, we will talk about it, that is essentially the pH, certain monovalent cations. Then you have solid state electrodes, solid state electrodes. These solid state electrodes are based on inorganic crystal or recently conductive polymers. Okay. We may not have a scope really to go through this, okay, but just have an idea. Inorganic crystals, or you have conducting polymers. Then you have liquid based electrodes, then you have compound electrodes. I am not getting into the details of it, but just I wish you have an idea. Compound electrodes. These are the different kind of ion selective electrodes. What out of them, one or two we will be dealing with. Now, let us talk about a metal electrode, where we started in the last class. Okay. So, one of the metal electrode we will talk about today, metal electrode is the one which is used for measuring Ag plus ion concentration. Okay. So, the most common metal indicator electrode. So, we have already talked about the reference electrode and the indicator electrodes. Okay. So, now we will be only concentrating on the indicator electrode, of course, with respect to our three different kind of references, either hydrogen or AgAgCl or calomel. These are the three reference we have already talked about. So, we are not going to get into that anymore. So, now we are talking only about the indicator electrode, okay, metal indicator electrodes. So, one of the major indicator electrodes which are being used, most common metal indicator electrodes is platinum, and then you have gold. Okay. these are relatively inert, and basically it does not participate in any chemical reaction. Its purpose is simply to transmit electrons to or from species in solution. Okay. To suppose you have the platinum indicator electrode, either it will pass the electron like this to the solution, or from the solution it will pick up the electron and it will pass it on. Okay. So, on the other hand, if you look at it, selective binding happens in the ion selective electrode. Okay. Now, these are basically relatively fairly inert and do not participate in chemical reactions. Its purpose is simply to transmit electron to or from species in solution, okay, either to the solution or pulling the electron out of it. Gold electrode are even more inert than platinum. Okay. Various type of carbon are used as indicator electrode, because the rate of many redox reaction on the carbon surface are very fast, and you see a lot of work is currently happening on graphene oxide, reduced graphene oxide based carbon electrodes, carbon quantum dots, because the electron really moves through in a very rapid pace. That increases the sensitivity as well as the efficiency of the system. Okay. So, this is what an electrode out here does. A metal electrode works best when its surface is large and clean, okay, and there are several techniques to clean it. So, what we will be talking about a silver electrode that can be used with a reference electrode to measure Ag plus ion concentration. The reaction at the Ag indicator electrode is Ag plus. So, you always have to have a practice of writing these reactions. Ag solid, where E0 plus is equal to 0.799 volt, and with reference to an calomel electrode, we have already talked about calomel electrode, calomel reference electrode, which is Ag2 Cl2 solid plus 2 electron leading to 2 Ag liquid plus 2 Cl minus, okay, and here E minus is equal to 0.241 volt. And if you have to picture it, it will be something like this. Here you have the reference electrode sitting there, double junction saturated calomel electrode Ce, standard calomel electrode is Ce, what we have talked about. Here you have the voltmeter, you are measuring the voltage, and here you have the Ag wire, okay, and the solution has the analyte is Ag plus aqueous. Now, if you know under a known condition the voltage, now if you change the concentration, if you add more of Ag plus into the solution, then the voltage is going to change, and that is exactly what you are going to measure. So, now if you look at it, the way the equation will pan out will be E is equal to E plus minus equals to, we have already talked about the values, right, 799. Okay. Now, let me plug in the values. The values will look like something like this, 0.799 minus 0.0596, okay, is log 1 upon Ag plus, which is your analyte you are trying to look forward to. What you have to find out, minus 0.241, which is this value, which is potential of the standard calomel reference electrode, and this is essentially your potential of Ag plus indicator electrode. So, now if you calculate E is equal to 0.558 plus 0.05916 log Ag plus. Now, this is your unknown. Now, if you know this value, which will be shown by the voltmeter, you can tell how much analyte is added into the system. So, if you know the known amount, then you can always back calculate and figure it out. So, this is how metal electrode works, and as long as you have these reactions straightened up in your brain, you can always calculate what is the voltage, what is being obtained. Okay. So, this is one example what I wanted to show you. Now, from here I will move on to another example of ion selective electrodes. Okay. Now, let us talk about the ion selective electrode, but before I move on to the ion selective electrode, there is a concept which I wanted to introduce, is called junction potential. What is junction potential? Junction potential is essentially when dissimilar electrolyte solution are in contact. When dissimilar electrolyte solution are in contact, a voltage difference called junction potential develop at their interface. This is a situation you will observe when you have a salt bridge, which has a different electrolyte, okay? Electrolyte B, and you have an electrolyte A, you have a electrolyte C. Okay. Now, whenever dissimilar electrolyte solutions are in contact, a voltage difference is created across this, which is called the junction potential. This is small voltage, usually few millivolt, is found at each end of the salt bridge connecting the half cells. The junction potential puts fundamental limitations on the accuracy of direct potentiometric measurements, because we usually do not know the contribution of the junction to the measured voltage. Okay. So, E observed is equal to whatever the E, whatever you have the two electrode, you have the E which you are measuring here, E observed is equal to E cell plus E junction. So, you will always have a junction potential, because the junction potential is usually unknown and E cell is slightly uncertain. So, essentially why junction potential occurs, if you consider an NaCl in contact with distilled water and NaCl ions begin to diffuse from NaCl solution into the water. Say for example, you have an, this is the situation, say for example, NaCl solution, here you have the water solution, and both Na ions and Cl ions are diffusing out. Okay. Both Na and the Cl ion begins to diffuse from NaCl solution into water. However, Cl ion has higher mobility than sodium ions, that is chloride ion will diffuse faster than sodium. So, as a result, a region rich in chloride with excessive negative charge developed at the front. So, what will be the next picture will be something like this. You will have negative, 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 negative at the front and positive, positive, positive at the back. The positive are coming from the sodium and the negatives are coming from the chloride ions. Behind it is a positively charged region depleted of chloride. This result in an electric potential difference at the junction of NaCl and water phases. So, this kind of situation lead to a junction potential. The result is an electric potential difference at the junction of NaCl and water phases. The junction potential opposes the movement of chloride and accelerates the movement of sodium. The steady state junction potential represents the balance between unequal mobilities. So, there is an unequal mobility what is being highlighted here, that creates a charge imbalance, and the tendency of the resulting charge imbalance retards the movement of chloride ions. Okay. So, this is a classic case of junction potential what I wanted to highlight, and these kind of junction potential problems will come time and again as you will be doing practical experiment in this area. Okay. So, having said this, now we will move on to next class onto the ion selective electrode with one example of ion selective electrode. Then as we promised, we will talk about oxygen electrodes, we will talk about the pH electrode, and we will talk about the glucose electrode. Okay? Thank you.